Good morning good afternoon to all of you. In the today's class, I am going to discuss about implementation of tokens in lexical analysis. So in the previous session, already we discussed about what is the lexical analysis. So that is how it reads the characters and how it forms the lexems, tokens, and the regular expressions, and I solved some of the problems on the regular expressions. So in this class, I am going to deal with regular expressions to finite automata. So in the finite automata, so there are two types, that is a deterministic finite automata. So non-deterministic finite automata, regular expressions to NFA, so NFA to DFA. So designing finite automata from regular expressions and some problems on that topic. Finally, I will explain some gauge or degree college lecturer, DL and MNC company problems. So first thing is, you see that the tokens are recognized by regular grammar. So the tokens are recognized by regular grammar. So in the previous class, in the previous session, already I discussed about the tokens, how the tokens are forming, what are the regular expressions, what are the regular languages, like this. After forming the tokens, so then you have to see that whether the tokens are producing correct results or not, either the token is accepted or not. So if you want to see that implementation part, so the tokens are implemented by finite automata. Tokens are implemented by finite automata. That is the overall structure. First you see that the regular expression to finite automata, high level sketch. You see that high level sketch, how the, so that is the lexical compiler. So that is the implements tokens by using finite automata. So the first one is, so the first and foremost is lexical specification. Lexical specification. So in the previous class already we have studied about lexical specification. Here in the lexical specification means the recognition of tokens. Recognition of tokens. That means the lexical analyzer scans the input string. So from left to right, character by character, and forms the lexems. So that is the based on the these lexems. So takes the these lexems converted into tokens, and the next tokens are verified by the lexical specifier. So that means after forming the tokens, so the next one is, so we are creating regular expression. Suppose we are using regular expression. Suppose all the tokens are formed into a regular expressions. So already we have studied regular expressions in the previous class. So from this regular expression, so we convert that into NFA, non-deterministic finite automaton. Non-deterministic finite automaton. But here is the non-deterministic finite automata is a theoretical concept. But here is we cannot implement, or we cannot write any program for solving. So later on I will explain that why. So that is after that the NFA is converted into DFA. After that NFA is converted into DFA, deterministic finite automata. So from this deterministic finite automata, so then we can convert that into table driven form. So then we can convert them into table driven form. So the table driven form is, so the table driven form, that means we can form the table. So but here in the table is nothing but, so that it contains the rows and the columns. So but in computer, if you want to write any program, it is very easy to implement and write the program in any language for, so that is performing operations on the tables. So this is the overall structure of, so that is how the lexical analyzer works, and how that will be identifying the tokens, and how that will be implementing the tokens like this. So for example, generally in the programming languages, but whenever are giving input is a string. So suppose if are given input is a string, so that string is automatically internally the lexical analyzer that will be, so that is they scan the strings and separate them into characters, from characters to lexems to tokens. So after that, the tokens with the help of the tokens, the regular expressions are formed. Those regular expressions are converted into NFA, from NFA to DFA, DFA to tabular form. So whenever I get the tabular form, so then it is very easy to implement. So and find either given string is accepted or not. So now we'll see that. So that is already we have studied the lexical specification, regular expressions, and now we'll study about NFA. So that is what I mean by finite automata. So that is the finite automata. So it is an abstract machine which accepts string as input and find the given string is accepted or not. It find the whether given string is accepted or not. So that is, it is an abstract machine. That means it is not a concrete one. So that means it will not show clearly about what function is going inside. So, but in the concrete machine, everything should be visible. But in this case, here it is an abstract machine, means so that is everything is simplified and everything is hidden from the people. So it is an abstract model which accepts string as input and finds that the given string is accepted or not. That means the final state of the finite automata is either true or false, either accepted or rejected, either 1 or 0. So that is the finite automata. The finite automata consists of the following things. So formal specification of mission is, the formal specification of mission is this one, Q, epsilon, so that is the small q, f and tau symbols. So here is what it represents. But whenever we are using this finite automata, we can implement this finite automata in 3 ways. So first one is we can implement it by using transition diagrams. Our second one is we can implement it by using the regular expression formulas, by using regular expression patterns, or by using tables. But using these 3, any one of these can be used for implementing the finite automata. So that is the formal specification or definition of that finite automata is this one. So that is the what is the Q? Q is a set of a finite set of states. So when you are using the transition diagram, so that is the key is a finite set of states. And here is sigma. Suppose when you are using the sigma, a set of input symbols. We can use set of input symbol. So what are the set of input symbols? That is the any character set in the programming language. But here is we can take some symbol, or suppose if it is a number, we can take the symbols. So that is a binary number 0 to 1 or something like this. So next key is the initial state. Within the transition diagram, we'll have key is the initial state. And every finite automata, every mission that will having only one input state, and it may be having any number of final states. It may be having at least one or any number of final states depending upon the problem. So next, this is to specify the transition function. Here is, suppose there are set of states are there, so that is the machine will move from one state to another state. So based on the input character, so suppose input character that will move to the thing, that movement, that the transition will be represented with this 2 functions. So that means this is the thing. For example, you see this. So here is this is the so the transition diagram, or that is a finite state machine procedure. Here is when you are seeing that Q, finite set of states. So how many states are there here? That is the state 1 and another state. But here is we are having, so that is the 2 states. So that is the state 1 and state 2. So next, a set of input symbols. Sigma is set of input symbols. But here is input. For example, you see that. So that is the 0, 1. So that is, these are the input 0 or 1. So in that case, for example, here is So in the case of first one, we are using 0, comma 1, 0, comma 1 states that will be having. Or so suppose here is, suppose whenever you are using that, are set of input symbols. So that is what are the input symbols we are giving? Either 1 or 0. That means it is a binary set alphabet. It is a binary set. So alphabet. Here is, we can say that it is a binary, so that contains only either 0 or 1. We can use either 0 or 1. So these are the input states of the, so that is the symbol. That means alphabet on finite automata. So key is a final state. So key is a final state. In this case, and we can say that this is the 0 is the final state. Suppose here is, we can say that the 0 is a final state of this. And here is, so F set of final states. So that is the final state always represented with double circles. The final state, so always represented with a double circle. So for example, here is when we are using this, suppose here is, so whenever using this, so suppose here is 2 states are there, but here is only one final state. So that is the, so then here is you can use, in some finite automata we can use Q1, Q2, Q3, but here is taken 0 and 1. So next here is the transition function. When you are using the transition function, so suppose when you are given the input that enter into the final state. So that is on input 0, so the mission will be moved from 0 state to 1 state, 0 state to final state. But while the mission is in the first state, so suppose when you are given the input is 1, it will be remain in the same state. So this is the, so that is the final finite automata of this one. So have you understood that? But I think already have studied about finite automata. So that means I think Professor Rajshekhar sir taught that subject. I heard about this. So then here is, I don't want to go in depth about this finite automata, and I will explain how the finite automata will be used for implementing the tokens. I understood that. And here is, it is an abstract mission which accepts string as input and find the given string is accepted or not. So that is a finite automata consists of the following things. So formal specification of mission is, so that is a set of symbols, that is a Q, capital Q, sigma, small q, f and delta function. So that is the tau function, that is the delta function, tau, we can call it as tau. So that is the Q specify that a finite set of states, That means, so that is the total number of states will be specified in the Q. And set of input symbol. Suppose if you want to move from one state to another state, you have to give some input values. So that means here is we can specify the input string, either alphabets or suppose digits or something like this. So Q is initial state. So every finite automata contains the initial state is only 1, and the set of final states, so that is equal to 0 or any number of final states, 1 or any number of final states it contains. Delta is a transition function. So that means, so suppose when you are given that, so suppose when you are given the input either 0 or 1, it will move to, so the next state. So here is when you see that finite automata. So there are two types of finite automata. So one is a deterministic finite automata and another one is non-deterministic finite automata. So the deterministic also called as a DFA, that is a non-deterministic finite automata is called, so that is the NFA. So in a DFA, so briefly I will explain this. In a DFA, so for a particular input character, the mission goes to only one state, In a DFA, for a particular input character, the mission goes to only one state. So on single input, it should not go to more than one state. So that's why we are saying that it is a deterministic finite automata. So a transition function is defined on every state, for every input symbol. That means here is that means here is whenever taking the deterministic finite automata, so it start with the starting state and it must enter into the, so that is the final state. Then only we can call it as the accepted, or otherwise it will be rejected. That means a transition function is defined on every state for every input symbol. So in DFA, null move is not allowed. Suppose when you are implementing the DFA, the null moves are not allowed. So it doesn't contain epsilon. DFA cannot change states without any input. So DFA cannot change state without any input. Suppose if you want to move from one state to another state, so compulsory you have to assign one input character. So based on the input character, so the machine will decide to which state it has to go. So next one is, suppose, so for example, you see that, so that is the below is the DFA with sigma 0 comma 1. Here is the sigma is the alphabet. 0 or 1. 0 or 1 means that is the binary string. We are saying that it is a binary string. That is, if you want to form any binary number, we can use only 2 digits, 0 or 1. If it is a decimal number, 0 to 9 we can use. Suppose if it is a string, I can use the small a to small b, small a to small z, or small capital A to capital Z, depending upon the problem, right? Accept all the strings ending with 0, 0. For example, below DFA with epsilon is equal to, so that is a 0 comma 1, accepting all the strings ending with 0. So in the previous class already, so I explained the language, that is the string which contains all the different kinds of problems. For example, suppose you take any string, for example, if you take any string, so here is, suppose if you are taken that is a 1, string is 1, so suppose here is take 0, 1 or 0. You take any string, the last 2 digits must be zeros. Last 2 digits must be 0. Either you can give like this, 0, 1, 1, 0, 1, 0, 0. So that means these are the strings we can give. But when you are given the strings like this, so then whenever given the string, so first one is, you see that first it will take, so this is the transition diagram, or you can call it as a, so regular expression. We can write this is, suppose if you want to get this 0 or 1, 0 or 1 star 0, 0. That means, so that is, it may be contains any number of zeros or any number of ones, but the last 2 digits must be 0, zeros. So in the previous class already I explained that regular expression, that is the 0 or 1 star 0, 0. So for this one, when you are drawing the transition diagram, so the transition diagram is nothing but, so the implementation of NFA or DFA. But here is, if there are no epsilon moves, but here is only one final state, so then we can call it as a determinant. Suppose you see that no epsilon moves and the final state. Suppose when you see that, here is the 0 is the first state, and suppose if you consider the string, so suppose if the input is, in this case input is a 1, it will be in the same state. Or so suppose another, it takes another 1, so another 1 is also in the same state. Suppose when you are taking that is 0, if the input is 0, immediately the machine will move from state 0 to state 1 on given input 0. So next one is, immediately we are having 1. 1 means again that will comes to this next 0 state. So after that 0, 0, compulsory is 0, or next one is the 0. So then the string is accepted and it is correct. And the machine will say that the string is accepted, like this. But here is when you see that one important thing is to note, the one important thing to note is there can be any possible DFA for a pattern. Suppose when you are taken, this is the one pattern. So for this one, you can write any number of. So suppose here is the only, I written only one string, I had drawn the only one transition diagram. It may be contains more than one transition diagram. So we can draw depends on more number of transition diagrams. But when you are using the more number of transition diagrams, so our aim is what? So we have to produce the optimal solution. We have to produce the optimal solution. How do you get that optimal solution? So with the minimum number of states. But when we are implementing this with the minimum number of states, definitely it increases the execution speed and it also avoids the confusions. And so that's why the memory is also occupying very less. That's why. So this is the so that is the DFA. I've understood that in the DFA, with the given any regular expressions, well, first we can draw the transition diagram. That means we are converting the regular expressions into, so that is the NFA to DFA. So the latter will show that. So that is the DFA. In this case, so for the same regular expressions, we can write any number of transition diagrams. But among those, which state diagram, so we'll take the minimum number of states that will be considered for execution of the tokens. So second one is non-deterministic finite automata. So but in FA, NFA is similar to DFA except following additional features. So one is null moves is allowed, but in the NFA, null moves are allowed. That means whenever you are giving the input as epsilon, it moves from one state to another state without any. So that means without giving with giving the epsilon, it will move from one state to another state. It can move forward without reading symbols. So that is without reading input symbols, it can move from one state to another state. So second one is ability to transmit to any number of states for a particular input. So suppose when you are given the input, so that is for one input, it may be having any number of final states. It may be go to next state 1, state 2, state 3 like that. So but in DFA, that will be go to only one state. That will move to only one state. So next here is above features. But when you are taking these two features are extra than DFA. But when you are adding these null moves so that is moving from one to many states, is there any advantages? So that means here is these above two features do not add any power to NFA. So suppose when you are implementing that NFA, so null moves are more than one state, move to more than one state. So for a single input, these two are not increasing the power of NFA. So due to above additional features, NFA has a different transition functions. So the rest is same as DFA. Because only these two, so the non-deterministic and deterministic will be differentiated. But why we have to use it? So the main advantages of using the non-deterministic finite automata is, suppose if there are 3 or 4 regular expressions are there. If there are 3 or 4 regular expressions, we can combine them by adding null moves. By adding null moves, we can connect all the regular expressions or all the characters within the string. That is the only advantage of using deterministic finite automata. So from this deterministic finite automata, we will convert the DFA. So suppose here is when I think you understood that, right? Suppose you see that. So the for example, below is a NFA. So in this case, if any path for an input signal, input string leads to final state, then the input string is accepted. So that is our idea is, so for any input string, if it reaches to the starting state to final state, we can say that it is accepted. Otherwise, it is not accepted. So for example, you see that in the so that is NFA. So for when you are given that here is the two states are there, 0 and 1. When you are given the input 0, suppose 0, it will be remain in the 0th state, or otherwise it will move to state 1. Where on the given input 0, either it will be remain on the 0 state, or otherwise it will move to 1. But here is some ambiguity is occurred. Either you have to stay within the state or go to the state 1 or final state. So that is the NFA. For given one, so that is the only one is there, only that will be remain in the zeros. So to avoid this confusion, but when you are using this kind of ambiguity, if this kind of ambiguity, it is not possible to implement by writing the programs, that is the Lex programming. But actually we know that, so every instruction must be definite. We think that, so that is in the already that is the algorithm rules, no? Every instruction must be, so that is the finite or definite. Definite means there is no ambiguity. But when you are using the NFA, so there is an ambiguity is there. To avoid that ambiguity, we can go for DFA. We can go for DFA. That's why. So in the diagram, I will explain So the lexical specification, lexical regular expressions, NFA, NFA to DFA, DFA to tabular form. After that, we will write the program for tabular form without confusing, right? So here is suppose the key points between NFA and DFA. Every DFA is not NFA. Every DFA is not NFA, but not, so that is every DFA is NFA, but not vice versa. Sorry. Every DFA is NFA, but not vice versa. That means every DFA is a NFA, or every NFA is not a DFA. So that means, so that is then here you can say that NFA is a theoretical concept and DFA is a practical, that is the concrete concept. So there exists an equivalent DFA for every NFA. So there exists an equivalent DFA for every NFA. So not for an every NFA. So this statement is somewhat wrong. So both the NFA and DFA have same power, and each NFA can be translated into DFA. So there exists, suppose there exists an equivalent DFA for every NFA. That means, so only some DFA can be implemented from NFA. Here is both NFA and DFA have the same power, and each NFA can be translated into DFA. But when you are using that, you may think that, so that is which one is the best. So here is both are same. So according to execution speed, according to analysis, so the both are same. So that's why there is no difference between and the NFA and DFA in the power of calculation, in the power of execution. There can be multiple final states in both DFA and NFA. There can be multiple final states in both DFA and NFA. Already I explained that. There may be only one initial state and there may be any number of final states. So in the NFA or in the DFA. But you remember that for given input in DFA there is only one, it will move to only one state, but in NFA it may be moved to more than one state. Only that is the difference. So these are the key points of this. NFA is more of the theoretical concept. Generally, NFA can be used for description about the finite automata mission. And DFA is used in the lexical analysis in compiler. So that is in the DFA is used in lexical analysis in a compiler. Suppose in the compiler design, in the lexical analysis part, so we can use in the lexical compiler uses DFA, not NFA. So that means only NFA is used to convert this one. Suppose here is conversion from finite automata to regular expression rules. Initial state should not have any inputs. Suppose when you are using that, initial state should not have any inputs. If S, create new initial state with epsilon. Create with new initial state with epsilon. So that means input state, suppose when you are mentioning that input state, so if there is no input value, so then you have to create a new state with the epsilon moves. So second one is, so final state should not have any outgoing state. So final state should not have any outgoing state. So suppose from that, sir, that is the final, but no outgoing states are available. Suppose when you are using some outgoing states, sometimes you can call those are the dead states, right? So if yes, create new final state with the epsilon. For example, here is I am saying that suppose there are three. So suppose there are three final states. If there are three final states, so we can combine the three final states by creating new state by adding epsilon moves. By adding epsilon moves. So that is more than one final state, create new final state with the epsilon. With the epsilon. So these are the rules for writing conversion from FA to regular expression. Epsilon moves. You see that some of the examples I will explain after that. So suppose epsilon moves. So that is another transition is epsilon moves. That is the mission can move from state A to state B without reading input. For example, you see that. So that is the A is a state and B is another state. So here is, so on this transition, so that is an arrow marks were representing epsilon. So that means when you are given the input is epsilon that move from A to B, epsilon is null. So without giving any input character of input string, it will move from one to other one. So this kind of transition we can write. This is the epsilon move. Whenever comes that epsilon move, without mentioning any alphabet of sigma, it will use the only from A to B like this. For example, here you say that it is a one of the acceptance NFA. Suppose, for example, here is non-finite, so that is non-deterministic finite automata. So either the string is accepted or not. You see that here is an NFA can get input into multiple states. So most of the examples I have taken from, so that is Ravi Sethi, the compiler design and the Woolman. So these examples are available in the Ravi Sethi or so that is the Pullman. So that is the prescribed text. That is also those are also standard textbooks for compiler designs. And NFA can get into multiple states. For example, so you consider this. Here is, so suppose on given input 1, here is 3 states are there. So one initial state and one is the final state. For example, here is on given input. So given input 1, it will be remaining in the first state, So suppose on a given input, it will be remain in the first state or it will go to the next state. It will go to the next state. Suppose if I assume that it is a 0 state, it is a 1 state and it is a 2 state, from 0 state to 1 state it will go. So suppose from 1 state to, it will move to final state on input value of 1. So here is, but in this case you see that, for example, if you want to see that 101, either the 101 is accepted string or not, either it is accepted or not. First you see that, so this is the initial state. First it enter into the initial state and it reads the first character. First character is what? 1. But when you click on that 1, so that is the input is 1. Here you see that input is 1. So it moves to this place. That is remain in the same state. Remain in the same state. So after whenever giving the 0, so that is the input here is I am reading input 0, that moves to next state. That moves to next state or remain in the same state. So that is you have to take the decision. But there is some confusion is there, but you can't write any program for implementation of NFA. So after that, when you are given that is a 1, so then that will go to the next state. But here is, so that is in the NFA, when you are given the string is 101, it is moving from initial state to final state. It moving from initial state to final state. So then the string is accepted. Then the string is accepted. But here is when you are using this theoretically, but here is the two concepts are available. On the basis, either suppose in the system, but as a human being, so we can go from 0 state to 1 state on input 0. But how the system will identify, how it is ambiguity. So there is a no definiteness in the statement. So that's why the system will feel ambiguous, right? So that is the rule. NFA accepts if it can get in a final state. That means it is a accepted state. I understood that it is a NFA. So here is, so that is the most of the cases, but actually why you have to convert that into NFA means, if there are any number of states or any number of sub-expressions, sub-regular expressions, all will be connected with the epsilon. That's why we can go for NFA. First you have to construct NFA from the regular expressions. After that, NFA to DFA, DFA to tabular form to program. So that is the procedure. For example, you see that there are two alphabets. That is the A. This is the regular expression. You assume that it is a regular expression of A and B. That is the input, two input symbol. So here is we can take that is a symbol A. That is the A is a one state and B is another state. These two are connected. So that is with epsilon. These two are connected with epsilon. These two are connected with epsilon. So for example, you say that, so the regular expression is A or B. When you are taking the regular expressions are A or B. So in this case, so we can draw the one regular expression A here itself, a symbol that is the A, and here is we can write B. So that means these two are separate states. Suppose when you are taken, these two are separate state. So then here is, so if you want to move from state A to next final state, A to final state, but here is, so these two are connected with the epsilons. We can use the epsilons. At the end state, these two are connected to the final state using the epsilon. So suppose here is, we are constructing that NFA. So suppose when you are constructing that NFA, it is very easy to find the optimal DFA. It is very easy to find optimal DFA. So that is, it avoids some confusions. Some confusions means, suppose if you want to combine two or more expressions, regular expressions, so NFA is better than DFA. So this is the NFA, this is the NFA. So next you see that A star, we can use A star. A star means what is the language it produces? So what produces? A, epsilon, and maybe star means that is the closure. Closure means start with 0 to any number n or infinite. Suppose it will generate the language A. So already in the previous class I explained that. So suppose here is whenever you are using, so suppose here is we can use A, 1A, or so suppose epsilon, that is the string, that is a language contains epsilon, that is the, there is no value, and the next one is you take that A, and the next here is the 3 is, suppose here is A dash up to N. So suppose we are generating the language like this, it may be contains 0 or something. But when you are using this, but how to convert that into, so that is NFA to, so that is the NFA. But you see that here is only one state is there, here is 3 epsilon moves we are taken, 3 epsilon moves. For example, A, so suppose it is the initial state is 0, without giving any input, that will enter into the state A, that is epsilon. So that is the epsilon. If that is whenever you find the, suppose A or next A, again that will go to the epsilon first 0 and the next to epsilon 0. So that is after getting that, finally with epsilon that will go to the final state. So from this, because here is, this is NFA for A star. This is NFA for A star. So here is, this is the initial state, this is the final state, and this is the A, so repeating, so that is epsilon 0 or something. Suppose here is, suppose A is epsilon, suppose input is epsilon, that will move to this place. So from this 2, directly that go to the state of final state. So that is because why are given this epsilon function? If an input symbol epsilon, so that will move directly from this without entering the state. So suppose A, so that is epsilon A, and this again if I are given epsilon, that will go to this place next A like this. This is the regular expression to NFA. That is A star of this. So that is some of the examples I am explaining. Suppose consider the regular expression. So in the previous class already we had derived this, right? So but not on binary. Later I will explain that on binary alphabet. Already I explained that I took the A, B values and this one. Suppose A or B ended with A. So that is in the previous class I explained that. In the same way, so consider the regular expression. Here is, so that is a 1 or 0 star 1. That means this meaning of this here is we are using the closure. Here is we can use any number of ones or any number of zeros or zero number of ones or zero number of zeros, but the string must be ended with 1. The string must be ended with 1. So then you can see that how do you convert that into a regular expression, that is the non-finite, so that is the non-deterministic finite automata. So in the previous class already I written the language for this, right? So I don't want to write again and again that language. So because so there is no blackboard for us. For me with mouse I am drawing everything. So for example, when you take this one language, so that is here is these two may be 0. 0 means that is a 1 is accepted, and the next two, so next one is 1 may be accepted. So that is the 0 1 may be accepted, or like this. So that is this is the infinite. So for this language, suppose when you are using this for this language, so then here is for this language we can construct the DFA. We can construct the DFA, NFA. Just you see that here is within this NFA. So for example, here is we are taken that. So C2E, so that is a 1. That means either 1 or 0. 1 or 0. That's why. So C2E move. Suppose if on the input it will move to C2E, on 0 it moves from D to F. And suppose here is for this one, so compulsory that is the final state. So that is the I to J. It will move I to J, and all are connected. So with the epsilon, all connected with the epsilon without any input. Suppose here is without any input. That means without any input means epsilon. With epsilon that will enter into the B state. So from B state to it will enter into the C state. And if it is a 1, that will move to epsilon 1. And next again that will go to this any number of values. So this is the NFA. I think that, but here is exactly, suppose if these are 0, suppose here is 1 is 0, suppose here is closure we are using. That means, so the 0 number of ones are 0 number of zeros, but only 1 is there. Only 1 means directly this epsilon goes to H and that perform the, so that find the 1. Or 2 means that will come to this epsilon, that is epsilon C, that is the 1 epsilon. Again that comes to this epsilon G state to A state to this state. So directly this is the procedure, right? So for 1 1, so how it will execute? State A to state B to state C, C to E, E to G, again G to A, and A to H. So then epsilon and next to H to I to J. This is for second case. So this is called NFA, where is we are converting this given regular expression into NFA. Have you understood that? I think you are familiar with finite automata. That's why so that is I am not going in depth about all these things, right? So this is the thing. So that is NFA to DFA. How to convert NFA to DFA? So directly it is not possible to implement NFA. You see that more number of states are there. It is very confusing thing. So suppose which state to which state we have to move. It is a very confusing thing. That's why. So here is this NFA should be converted into DFA, deterministic finite automata. For a given language, the NFA can be simpler than DFA. So already I said that for any given input, for any given language, NFA can be simpler than DFA. That means NFA means simply, if you want to connect that, so simply we can use epsilon and we can connect the states. So that is you need not to think because it is a theoretical part. But if you want to implement by using computer, so compulsory it must be in principle or in logic. Otherwise it is not possible. So that's why, for example, you consider the string, ending string with 0 zeros. First you see that, so that means input string, they are taken that every string ending with 0 0. So that means here is 0 0 means what 0 0? For example, when you are taking that string, so suppose here is, so then language we can construct like this. So suppose either that may be language we can construct like this. So suppose 2 zeros, suppose here is we are taken, so the language is like this. Suppose here is the regular expressions we can form like this, right? For this one, suppose, so here is either 0 or 1. That means here is we can write, so that is the 1 or 0 closer and 2 zeros. We can write 2 zeros. This is the regular expression. This is the regular expression. So that here is, that may be taking 0 0 or 1 0 0 or any numbers like this. Suppose here is 0 0 and 0 like this. So any language can be created like this. So in this case, but you see that either it is accepted or not. Either it is accepted or not. So first you are drawing this NFA. Already I explained this same. So suppose for given this is the input state and this is the final state, and here is the 3 states are there, and given input 0, it will be remain in the same state or it moves to the next state. 0 0 like this. This is the NFA, but this NFA is converted into DFA. You see that the equivalent DFA of this one. So the equivalent DFA is for the NFA is, you see that. But here is, there is ambiguity is there. And given input 0, either it may be go to the first state, that is the, so first state or 0th state. So that's why for avoiding that we can convert it into DFA, deterministic finite automata. For example, you see that, but the conversion is somewhat difficult. Suppose you require more analysis, mathematical thinking. So for example, you see that, so if DFA is, the input symbol is 1, it will remain in the starting state. It remain in the starting state. Or suppose whenever you are getting 0 as input, it will enter into the second state. It will enter into the first state and the second state. Or again when you are given the 0, that will enter into the final state. That will enter into the final state. On any number of zeros, it will be remain in the final state. Or suppose, so in the after giving 0, next suppose input string is 1 0 1, 1 0 0 1 0 0 like this. So but when you are given that, so suppose for the given input, suppose 0, suppose here is I taken the value, for example, you take input. So suppose you take that is a 0. So next 1 0 0. If we are getting the string like this 0 1 0 0. So the first one is it will enter. So first it will enter into the, so 0 means that will take 0 input, immediately that will go to the second state. So next 1 is there. 1 means, but when enter into the final state, the string will be accepted. But here is a 1 is there. So then again that come back to the first one. Again it come back to the first one. That means first one. After that 0 0 that will enter into the final state. This string is accepted. This string is accepted. This is, suppose here is when you have taken the 1 or 0 0 0, then again that will be accepting. So here is, but in DFA you see that for only one input it will goes to only one state but not more than one state. So for NFA we are converting that into DFA. I think you have solved many problems in the finite automata, but I don't want to go in depth, but simply I am explaining So briefing the things, NFA to DFA conversion. DFA can be exponentially larger than NFA. Suppose when you are in the DFA, so suppose for the single input it may be goes to 10 states. 10 states in NFA. But in DFA, so 10 separate states must be created. So that's why here is the memory may be wasted or sometimes the execution speed may be reduced in the DFA, right? So that is NFA, DFA example. The same already we have taken that NFA and how to convert that into DFA. For example, in the same thing you see that. So this is the NFA. First you have to convert this NFA into DFA. For example, you see that an input states 0. So suppose on 0 state, suppose in the 0 moves, how it will goes to this? Suppose input is 0. Then that will enter in the final state. We have written F. After that G has written. Again it will go to the A state. So that is the A to B. Again we have written the B to F, so B to C. Next suppose for 1 but C, D, H. Either this one epsilon, C, D, H and I. That is the H. So suppose on this one directly it may go to the H and H, I and J values. For every given input, or suppose if you have taken that is the input is all the values you can wherever you find this in the A, B, C, D, I values. Here is wherever you are finding epsilons, we are keeping that. Here is suppose here is on 0th. On 0th it will go to the state F and like this. And 1 and on the process 1, so that will move to E, G, A, that is E, G, A, and the next that is the B. So that is the B to C, so that is the C to D. That will go to the either this one or this, or so suppose here is again that will come to this place C to D and J, and here is this is the equivalent DFA for NFA. Here is this NFA. First one is we can take the regular expression, we can convert that into NFA. From NFA to DFA we are converting. So that is after converting that NFA to DFA. Then you have to implement find the table. So for either you have to, based on this you can find that either so the string is accepted or not. For example, you see that it is the same thing. Suppose we are making it as a DFA, but here you see this. So this is the DFA. We are taking this 1 state, 2 state, 3 states because this is the minimal number of states I am taking. So that is here is when you are taking that S to this one and how to construct the table. And here is the table is constructed like this. For example, so here is, so that is here is you say that U is a final state. We are assuming that U is a final state because it is a double circle, and S is so that is the starting state. For the starting state we can show the arrow mark, and here is on the input symbol 0 and 1, 0 or 1. So suppose on 0, suppose either here is either these are the states. Suppose from S, when you are given the input is 0, either it moves to T state. When you are given the 0, it moves to T state. Or so suppose on input S, suppose if you are given the 1, that will move to U. So that's why here is written U and here is written T. And the next one is from T state, from T to L. Suppose when you are given the input string is 0, so that will be remain on same state. So that's why here is written T. And next on given input 1, that will enter into the state U. So that's why I mentioned the U. Or next that is the final state is U. Suppose, so that is the from U. So suppose on input of U, so suppose it will be goes to the state. So suppose there is a T, and next on a one put again that will comes to this place. So this is the table we constructed from the DFA. I understood that. So first here is you see that. So here is we have taken the regular expression. What is the regular expression here? 1. So that is the 1 or 0. So that is the star 0 0. That means here is any string accepting any string with the last 2 zeros. That is the thing. So for this language, for this string, we mentioned that regular expression this one. After that, we constructed regular expression to NFA, NFA to DFA. So after that, this DFA is converted into tabular form. Here is this DFA is converted into tabular form. So after that, you have to check it whether the given string is accepted or not. For example, with the transition diagram only we can see that either accepted or not. For example, here is the given string is 1001. I have taken the input string is 1001. Either it will accept or not. Suppose for all the given 4 input characters, if it reaches the final state, we can say that it is accepted, else it is not accepted. So in this case, first we can read the first character. We can read the first character. So that is the first that will be. So that is the mission will be always in the starting state. After that, first it reads the first character. So first character is what? First digit is 1. So then it will. So that is the input is 1, and that will enter into the state U. So that is on the input 1 from starting state. Input 1 that will enter into the U state. That is the final state. So after that, suppose next we are reading the 0. 0 means, so from this final state to, it will enter into the T state. That will go to the T state of this. From this again 0 is there. Again 0 means, so that will remain in the same state. That will remain in the same state. You see that will remain in the same state 0. After that, suppose when input is given 1, here is that will come to this place. That will enter into the place of this. So finally, so the last digit, when you are given the last digit, that is enter into the final state. That's why we can say that it is a string is accepted with this language. Right? I understood that. So suppose here is that we are given the string 1001. So either it will be accepted or not. But generally, what you will do, suppose through the keyboard, whenever I enter the values, in the Java program, always it takes in the form of strings. The strings will be converted into characters, and character is converted into binary form, and based on the binary means that is ASCII code that we'll be using, and 8-bit code. Suppose capital A, when you are taking that 8-bit code 0 1 0 0 0 last one. So but this string, either that A is a correct or not. For this one, so we can use the finite automation, and so that we can compare the strings. That is the main application of this one. So this is the accepted string or not. Suppose you say that the string can be accepted. Answer that here is in this case. So the string is 1001. First mission is in the starting state. I'm giving one input to input. It will enter into the U state. So I'm giving 0 that will enter into the T state. Again second 0 that will be remain in the same state. And the next one that will enter into this. This is the acceptance. But here the string is accepted with the help of that is the DFA. But the same thing, suppose in most of the finite automata, we can see that, so how the string is accepted or not. So that is, you can use the transition function. So that is the delta of S comma 1001. First we can take the S starting state 1001. So here is on one input value, string will be reading from left to right, character by character. Already I explained that. So that is the lexical analysis part. The lexical analysis, the string is read from the left to right, character by character. So that's why first it will take the 1, and here is that will enter into the 1. So that is the 1 means, so but when you are given the 1, that will enter into the U. So then here is you can say that delta U comma 0 0 on input 1 that will enter into the state. After that next input is 0. From this U, when you are using U delta of the U to 0 means that will go to the T state. Instead of T we are getting T state. Again 0 is from 0 state T on input of 0 that will be remain in the same T state, that is the T is there, and one output is 1. Here is the 1 means that will be taking, so from T to 1 means that will enter into the U, and there is a string is null. So then U is accepted. U is accepted. So that means this is the procedure so far either the given string is accepted or not. So in the same way, in any programming languages, it uses the character set, and when you type the character through the keyboard, So the same process will be done. After that, it will say that either the given character is correct or not, either given string is correct or not, given token is correct or not. Like this, for this purpose, we can use so finite automata. Have understood that? So based on this finite, suppose S to 1 or U, so that is output will be comes like this 0 0 1 of this one. So this is the string is accepted. I think in finite automata you solve many number of problems. So that's why. So now, so that is now I am explaining the values of this. So some of the problems on the finite automata. So suppose how to convert the regular expressions into finite automata. That is the either deterministic or non-deterministic. So that is either deterministic finite automata or non-deterministic finite automata. For example, you see this problem. So first I will explain some of the problems. Designing finite automata from the regular expressions. So that is we can design the finite automata from regular. So that is the DFA. Then with the finite automata only we can implement the code, right? So that is, you see that first question, even number of A's, even number of A's. The regular expression for even number of A's is. Already in the previous class I derived this. That means only you take any string in the language, so that is the regular language, you take any string, that string must contain, so that is the even number of A's, even number of A's. That means either it may be contains 2 values, 2 A's or 4 A's, 6 A's, 8 A's, so that is the 10 A's, 12 A's up to n. So for this purpose, this is the regular grammar. This is the regular grammar. Just you see that. So here is I am taking. Here is also that is a whole. So that is here is the cleaner is there. Suppose A and A. So for this one, suppose when you are using that, so that is here is also B star should be there, but no B star, but whatever it may be. Just finite auto we are written like this. But here is also we required some. So suppose here is also we can write. So that is the star of this, and here we can write star. Otherwise, so that is without confusing, the outside is also that is the closure is there, so that's why it may become 0, right? So but here is suppose when you are using that, so for this one the finite automata is, so that is 2 states are required, that is the minimal number of DFA, Q0 and Q1. So here is, so suppose the string should be always 0, but when you see that equivalent form, so Q0, suppose when you are given the input is A, that enter into the Q1, and next if you are given, so that is, so input is again A, again that will go to the Q1, again it will go to the Q1. So this is the Q0 is a final state as well as initial state. So sometimes the starting state may be final state. Suppose here is we required even number of A's. We required even number of A's. Even number of A's means we need like this. Suppose here is it requires A. Suppose A. Because so that is all the B's may be 0. Otherwise it may be B A. Or otherwise it may be, so that is the A 4 A's, or you can use the 4 A's, or next that is the B, or otherwise you can use the B or something like this. That may require 4A, 4A, B, R. So suppose when you count this, so 4 A's are not consecutive, anywhere you can get like this. Suppose AB of this one. Suppose here is the Q1. So then you say that when you are using this any number of values, so Q state, if on given input A, it will enter into the Q1, and if on given same A, that will comes to display. That means you see that. So when you are given in the initial state, when you are given the input A, that will enter the Q1. Suppose if you want to comes to final state, it compulsory it requires A input. So that's why A 2 A's, or 4 A's, or 6 A's, 9 A's. Suppose it may become any B. So suppose any number of B's that will be remain in the Q state, or after entering into this, suppose you are getting A0, so suppose here is A00 also there, right? Suppose when you are given that, so sometimes, so suppose when you are given, so suppose here is we have taken the B, or so suppose A, B, A, or next that is the B, A. So the string is accepted because here is A, two A's are there. So then it is accepting. So for this one, when enter into the B in the first state, for example, in the first state, when you enter into the first Q naught, B means remain in the same Q1. Suppose A, that will enter into the Q. So that is the Q1. So again B is there, suppose that remain in the Q1, and A, that again that will go to this place. Then a string is accepted. So that means it is a regular language. The what regular language will specifies. So the regular language contains a set of strings which are having even number of ones over the alphabet of sigma A comma B. But in this case, suppose if you want to find out whether a string is accepted or not, we can construct the DFA. After the transition diagram, we can find these things. So second one, you see that string with AB as a substring. That is the regular expression for string with AB as a substring. So suppose you take that is the language, regular language contains a set of strings. A regular language contains a set of strings such that each string must contain a substring of AB. A substring of AB. Suppose if there are 100 strings are there, 100 strings that those must contain AB as a substring. AB as a substring. So for this one, you see that AB, you are writing AB, and here is A or B closer, A or B closer. That means here is there may be any number of zero number of A's or zero number of B's or any number of A's or any number of B's prefixing, or after that any number of zero number or any number of A's or B's are there, and but here is you required only that two we required, so only this is the two values. Suppose here you see that, so AB should be required for this. This is the condition we can write. This is the grammar. So that means you can hear that a string may be contained. Suppose AAB, BAB. So that is the ABA, ABB or something like this, right? So this is the string. For this one, when you are constructing the DFA, so here is the first. Suppose whatever you have to find out the substring, it is a compulsory in all the strings. That's why we can write that is the A and B. Q naught A, Q1 B. So suppose on input of A, it will move to Q1, and next and B, it moves to Q2. Because whatever you have taken the strings, so these should be moved to one state to another state. But when you draw this, only 3 states are required. This is the minimal function. We can use any number of states, but minimum required, so that is the states are 3. Q naught is a starting state and Q2 is a final state. So, but here is, but when you are constructing the DFA, but you have to analyze whether the string is reachable or not. So first on each and every input, you decide. So it has to, it moves to which state. So suppose Q naught, if you are given input is A, so then that will move to Q1. If you are given B, that is in the same state, or Q naught. Suppose if you see that either given string is accepted or not. For example, so here is the A, B, C that is. But here is this may be 0. That language may be only I will write 1 or 2. So that is the A, B, AB. That is, this is, you assume that this is this one is the 0, 0. So the closures are there. That's why only AB comes. Or next, suppose A, B may be 0 or A. So suppose that is the string is accepted, A, and B. Here also substring is there. Or B, A, B, B, or otherwise you can use the A, B, A. It may be like this, BA or BA, B or anything like this. So, but when you say that BAB, whether the string is accepted or not. So, first one is that will enter into the string of this. Suppose here is, so B, when you are given the first string is B, that will be in the same state of this one. So, suppose when you are taking, so Q naught B, first is the B, so that is in the Q naught state. So second character A, that will enter into the Q1 state. Again you are given the B. So on input of B, it will enter into the Q state. This is the final state. So then the string is accepted. Have understood that? The second question. So third one is string with count of A divisible by 3. So that is in the regular expression already added. That is the string with the count of A divisible by 3. The regular expression for string with count of divisible by 3 is just we can add 3 means divisible by 3 means that is it may be having 0 times, that may be here is that may be 0 time or 3 or 6 or 9 or 12 etc. That means the number of states may be 0, 3, 6, 9, 12 or something like this, right? But here is when you are taking for this one, when you draw the state diagram, comes to like this. Same. So here it comes to A like this. So suppose 3 A's. Suppose when you are using that, so A to the power of 3n such that n is greater than or equal to 0, n is greater than or equal to 0 state. Suppose this is the final state. So suppose in remaining, so suppose when you are taking this, 0 no inputs if you are given, that is the epsilon. So then that will be in the remaining state. So A and A. So that is this will be find the. So that is divisible by 3. Suppose if I take that is a Q, A input is A, that will enter into the Q1. Again A, that will enter in Q2. Again A, that will enter into the Q0. Here is a Q0 is a starting state as well as final state. No, let's final state of that. So this is the final state of that. So next one is that binary number divisible by 3. The regular expression for binary number which are divisible by 3 is, so that is the 3 consecutive ones. Suppose here is examples of the binary divisible by 3 is 3 are 0, 0, 1, 1 means this is the 3, 1, 1, 0 is nothing but 6, 1, 0, 0, so that is like this, 9, 1, 1, 0 is a 12, or next that is the 15, etc. 15, 18, etc. So that is the DAP corresponding to binary divisible by 3 is the same thing. Same sum. So instead of 0, instead of A is, here is we can take A. So for accepting this, suppose here is, here is you can take the 0. But while I am drawing this diagram, but I forgot on this, so that's why extra symbol I put that is 0. So in this case, for example, you take this string, you take the second string. So that is here is I am taking, for example, so that is I am taking this string. Suppose when you see that, so suppose either that is accepted or not. For example, when you are taking that, you see that first one is you take input is a 1. So that is as a Q0. If on input 1, that enter into the Q1 state. That enter into the Q1 state. So that is after that again you are giving 1. Again that will enter into the input state of this 1, 0. So 1. After that we are giving next is a 0, that is the remaining same state. 0, that is in the remaining state. So 1 we can call it as a, so its string is accepted. Right? So that is the string. The binary string, so that is the first you have to convert that, so the decimal number into binary, and for that binary you can draw the finite automata. But here is when you are writing deterministic finite automata, by using any programming language, it is very easy to implement. But how many conditions we have to use? So suppose on Q0, it will enter into this. Suppose Q0, we can take the Q0. So that is if Q naught is equal to 0, so that is in the outprint Q naught. If the Q naught is equal to 1, that will enter into the Q1 like this. That is the, so that we can accept the string like this. So the later I'll explain that binary forms, but I think yesterday the time. So string with regular expressions. Suppose you see that a string contains regular expression 110 plus 110, that is the 5 ones closer. 1110 plus 1. So for example, you see that it is a regular expression. You have to convert that into DFA. You have to convert that into DFA. That means you have to convert that into transition table. Transition table to, so the transition diagram table. But here is but conversion of table is very easy. But only that is writing of that transition diagram is somewhat difficult. That's why I am explaining this. Oh, here is, so but when you see that either 3 ones or either 5 ones, star, that may be 0 or anything. Suppose here is when you are taking that accepted using the regular expression will have 3. So that means either this one, only if you come to this one 3 comes, or suppose either this, it may be 0, it may not be considered, or this may be considered. That is the 5, it comes. Or next, suppose when you are taking this, suppose 5, 6, suppose you are twice. So suppose when you are using, so 3, so you can write 3, 3, that is the 6. So that is the 6 ones are coming. Also suppose here is, so 3 ones plus 5 ones, that is when you are concatenating these two, so then here is it will come to 86, right? So next 8, also suppose 9 means, so that is the 3 times this 9, or so that is the 10 means, this is the 6, right? So suppose 5, and next this is the 2 times that will be taking, all the strings will be getting this. But here is when you are using this string and all other counts for one after another. They all counts for one after another. For this one, how do you write the DFA? You see that DFA. So directly, so Q1, Q2, Q3 and Q4. So that means here is whenever that enter into the state, so one state is extra, 1, 2, 3. So suppose here is only the string may be contains 3 ones. 3 ones means 1 input 1 Q0 to Q1, sorry it is Q1 or Q1 to Q2, and next one put string that will enter into the final state, that will enter into the final. So then here is the 3 is accepted, and here is another input 1, and that will enter into the, suppose in second case, that is the 1, 2, 3, 4, 5, 6 or twice, that is the 3 or twice means, suppose you can 1, 1, 1, 1, 5 ones plus this one. So suppose this is accepted 1, and next for 1 to 5, 1 Q6, 1 Q7, 1 that enter into the final state. So that means here is the for 3 it accepts 5, 1, 2, 3, for 5 is the 5 string, it is another final state, or for 6 is there, 6 is also another state, and the next 8 is there, so that is also accepting. There is no 7. Suppose you can't get the 7 here. That's why in this case it will having 3 final states. There are 4, 1, so Q3, Q5, so that is Q6 and Q8 are the 4 final states, right? This is the DFA. This is the DFA for given input expressions. Question number 6. What will be the minimum number of states for string with odd number of A's? With odd number of A's. Odd number of A's means it requires one. Every string, every regular language must contain a set of strings. So that is the such that every string must contain odd number of A's. Odd number of A's. That may be string may be contains 1 A, or string may be contains 3 A's, or string may be contains 5 A's, or string may be contains 7 A's. That is the so. But when you are taking that, that is the, so that is a 7 A's or B's. So that it is a regular expression. You see that? So that is any number of B's, or any number of B's, any number of B's, or any number of B's, so whole star of this. So for example, when you are taking that, the closures. So if B is equal to B is 0 times, so then here is A and A is there. But here is when you are closer, when if you consider closer is equal to 0, we can get only 1 A. You see that? Only 1 A. Or next we can get So that is the 3 A's, 4 A's. For example, you see that. So suppose here is when you see that, so the closer is 0, we can get only A. We can get only A. That is, this is 0, and the entire thing is 0. So suppose when you are taking, so that is this is a 0 and this is A, so then we can write that one is the A, and here is the B is also 0, and you can write B star B, that is equal to AB, or here is, suppose you can take A, or otherwise we can take, so B, A, B, A, B, A. This thing may be accepted like this. Suppose if you have BA, and B. Here is also 3 are there. Otherwise, you can use the, so suppose not like, suppose here is the BA, A3, or in this case A3, or sometimes you can use a 6 or 7 like this. 1 A3, or AB, comes like this. All are 0. But how to write the, generate the thing. Just a simple thing is, but these are very, very important for gate examinations. Later on I will explain the gate questions also. So suppose here is, you say that Q0. So 3 strings, that means, so suppose Q0, A, that will enter into Q2. So Q2 to Q3, again enter into A, that will come to this place. Suppose A, B is in the remaining state, and B is in the remaining state. So that when you execute this, automatically you can get the odd number of A's into 1 or 1. So that is the final state, right? So suppose first you take, that is the A is a string. So consider it, suppose A is a string. So suppose one, that is the string contains only one A. If this is odd, so then Q0, an input of A, it will enter into Q2. So this is the final state. But suppose if you have taken 3 A's, you see that 3 A's. Also suppose here is first that enter into the A, Q0, Q1, and again that will enter into the Q0, again that will enter into the Q1. But here is in this thing, so first if the input state is Q, first one is we are taking, that is the B. So suppose here is, so we are taking first, you consider that B. So B means that will be in the same state. Or so suppose when you are using that, so next A means that will enter into the Q1 state. After that B is there, that will be in the remain in the same state. Next A, again that go to the first state. B remain in the Q state, and A again that will enter into final state, and the next B that will be repeated. So that this thing is also simple. So this is the DFA. First you have to understand this, and based on that only you can draw the NFA to DFA. So but in the previous class I explained that is the variables, constants, so with the transition diagram. That is also nothing but the finite automata for checking the values. Here is the regular expression. You see the regular language L1 a to the power of n such that n is greater than or equal to 1. The language of the given one is, for example, if a to the power of n, language is a to the power of n, so that is n greater than 1 means L1 contains a set of strings, but all strings may contain all A's. Any length, suppose here is greater than or equal to 1 means the regular expression is what? So that is at least 1 A, triple A, 4 A's, 5 A's, 6 A's up to n A's. It is a finite automata will be like below. You see that. So first one is the starting state is a Y. Starting state is Y. When you enter that A, directly it will enter into the final state. It will enter into the final state. So but here is suppose A is there. So that's why here is, so then A. So A means that will enter into this place. The same thing that will be repeated. So this is the diagram for L1 a to the power of a regular expression. You see that. So regular expression L2 is equal to A to the power of n, b to the power of m, such that n comma m greater than or equal to 1. This is the regular language. So then for this one, so you see that is the language is like this. AB, or given that AB, AAB, that means AAB, ABB, AAABB like this. Suppose here is we have taken n and then, so that is if it is a 1, it is 0, it is a 2 or something like this. Already we know that. The final state machine is like this. In the first A, so that is a compulsory, that will be AB is there. So first starting state is X, and given input A, that will enter into the state Y, and here is that is the repeating. So suppose here is, so always all A's comes first and next all B's comes. So there is no chance of getting BA or something like this, right? So then here is A, B, and B means that will be repeating. For this language, we can construct the regular expressions BAB or something. Regular expression, that is here is you take the regular expression language L3 is equal to A plus B closure, A plus B star. That is the language of the given is. So suppose here is in this case, so closure, when you are using the closure, the epsilon in the language, in the grammar, it will comes epsilon. Suppose A is 0 or B is 0, so there is a 0, then epsilon will come. Epsilon, the regular expression is you can use epsilon, comma, A, that may be A, B, B, or something like this. A, B, B, only you can use B, B, or something like this. So then here is the regular expression is there. So for this one, simply we can write grammar with a single state. So that is the epsilon, that will always enter into this one. Otherwise, you can use the 2 or 3 states and we can draw the, that is the minimal thing is, we can use final state of A, epsilon, that is enter into the thing, and A and B something. This is the 10th one. So the construction of DFA for the set of strings over the A comma B such that the length of the string is exactly 2. Already I wrote the, so that is the regular expression. Length of the string is exactly 2 means, so alphabet is A and B. So then language is, that may be AA, AB, BA or BB. We can have only 4 things. For this one we can write the transition diagram like this. So suppose AA or AA, it will reach the final state, but after that when you are given the final state, that will enter into the dead state. That will enter into the dead state. Suppose you can give the AA, that will becomes AA, that will reach the final state, AB, that will reach the final state, BA, that will be AE, that will reach the final state, BB, that will enter into the final state. So after that, suppose when you are taking that is the other than 2, so that is the length 1, length 3, 4, 5, 6, that will enter into the dead states. So that here is, we can forget of the D is a dead state, right? So that is in the diagram we can show that dead state means, so that is we should not move from current state to next state. Whatever you give the input values, only that will consider these and that will be ignored. That is the dead state. So construct the DFA for the set of strings over A and B such that the length of the string is greater than or equal to 2. Length of the string should be at least 2. String is at least 2. That means 2 to it will start. Suppose here is at least 2 means, so minimum value 2 strings. That is the AA, AB, BA, BB, AAA, AAB, or it is up to infinite. The rate transition diagram for this language will be like this. First that will be enter in the state A, AB, AB, and any number of ABs that will be repeated and seen. Suppose if that is 3 A's are there, first that will enter into the starting state A, on input A that will enter into B, on input A that will enter into this one, and again so 3 A's. Suppose BB is, so here is an input B that enter into the B state and an input B that will enter into the state. So that this is the diagram of DFA. Here is you can convert DFA. So DFA to here is you can construct the table easily. So suppose A, B, C, and here is you can use the input strings A and B. so that we can use the condition. 12th one is the construction of DFA for set of strings over A and B such that the length of this string is less than or equal to 2. So three cases are done the DFA. One is string length is exactly 2. So string length is greater than or equal to 2 and string length is less than or equal to 2. Here is the string length is less than or equal to 2 means, so how many strings that will contains? 0 strings, that is epsilon, not the question mark, that is the epsilon, and AA less than or equal to mention AA, so that is the AB, BA and BB. Or sometimes A or B also we can take, A comma B also we can take for this. I read in that method. The state chart diagram is like this. ABB as same diagram were taken for the same thing. ABB, BABAB, AABB less than or equal to 2 we are saying that. Regular expression pi value. For this pi only there is a no state, that is always in the starting state. So only the language of the regular expression L1 is equal to, so the null set empty string. That is the empty string. For empty string, its a finite automata will be like this. That is within the same state. 14. Suppose if it is a A, so that is these are included in our test. I took these things from the textbook number 2 or 3. So that is the A is the alphabet. Suppose here is the language contains only one value, but that is the only one. The language is contain only A. So that means here is you can use the X to A. We are not using any closures. A means that is the, so on input A, so the finite automata moves from X to Y. And 15th question you see that A or B, union process of two alphabets A and B. The language of the given regular expression is L3, A comma B, and the language contains A and B as the string. A and B are the strings, not all the A and B are the strings. So then you see that A and B, that will move A to B, or given input is A, it moves to X, and given the input is Y, that moves to X. But here is understanding the question is a very important. But most of the cases we can use. So suppose here is A and B are there. We can write the things like this. Suppose two arrows we can use. For example, on move A, suppose here is one can use move. So that is on A, it will move to this one. Or on B, it will move to this one. That means, so that is this is also. So that is this one is also correct and this one is the correct. But among these two, so then here is the first what I have done. So that is here is, so this one is the minimal optimal. That is the only two states and only one transition signal we are saying. So that is easy. But you can represent like this, right? So this is the, so that is here is when we are using this. Erase the things. So 15 is okay. So next 16th question, you see that A dot B, concatenation of two alphabets A and B. For this one, how to draw the, so the transition diagram and DFA. The language of given regular expression L4 is AB. That is only it becomes A and B. A language contains AB as the string only. Only the language contains only one string, that is AB. So then here you see that simple thing is X on input A, it enters into the Y, X on input A. So the machine will enter from X state to Y state. On input B, that will enter into the again that final state, or Z, or you can call it as Z, or you can take the same thing as Y. So that is the Z that will enter into the Z. It is a final state. Or only A closure. So that is a clean closure. A clean closure means here is A to the power means 0. So suppose here is, so the language of the given regular expression alpha is equal to all the things, that is the language containing epsilon and any number of A's. But this is a very important, you see that. But actually when you are given that immediately, so you should not write the language. But here is, but this is a very important thing. Suppose here is, this is very important, understand. So suppose in every finite automata and the language processor, they can write like this. So here is, this is a very important one. So that is a language contains epsilon, or lack of the symbol, I kept that E, not that is epsilon, not E, that is epsilon, and any number of A's. So suppose the epsilon symbol in the symbol table is not found, that's why I put that here. So that is, this language may be contains, so the null A's, the null A's are 1A, 2A's, 3A's, 4A's up to 10A's. That strings may be contains 2A's, 4A's. That is, for this one I can use, so W epsilon. This is a DFA, but here is also we are using some epsilon. Suppose on input epsilon, that will enter into the, so X state. If I are given A, that will enter into the Y state, and again that will enter into the F state and epsilon, and this is called NFA. So suppose here is we are constructing that NFA, because with the epsilon moves, it moving to this. Suppose if you want to convert that into the same state, we can write like this, epsilon, and here is the state X, and here is A is there, no? So simply we can put like this, A to this, and here is, so here itself we can call, so then we can get it to the final state of this. So 18, the regular language L1, A into A plus B closure. The language of the given is, so that means the first character must be alphabet. That means any string start with A. Any string start with A. Any string start with A means, so then here is A. So we can use A or 2 A's, 3 A's, 4 A's, 5 A's or something like this, or A also 3 A's, or A, B, A. So that is the B, A. So that comes, this is the wrong, sorry, for example, that is the not that one. Okay, but it's sorry. Okay, it is not moving. No problem. That is, here is when you are using that. So that is the string we always start with A, B, B. Here is the A, and here is also we can use the B. The string always start with A, B, B, A, B, B, or something like this. So that's why here is we can use this value. So suppose arrow that enter into the A and B, that will enter into this one. So sorry, the string is wrong, but by mistake I entered this. So suppose the string start with A. So first this is Y is initial state. On input to A, that will enter into the Z, the final state, or this one. Suppose it is only one A is there. So suppose here itself they required. So suppose so here is the A is also one thing. A is there. A. Or so suppose AB. There are a number of strings are there. The strings always start with like this, but only I mentioned some of the strings, so that don't think it is wrong, but it is correct. Some strings only were taken. So that's why here is the regular language L2, A plus B star A. The language of regular expression is, so that is every string ending with the A. So before that, the string ending starting with A, and here is the string ending with A. So for this one, you say that. So suppose if you were given B, it is in the same state, or if you are given enter into A, that will enter into final state, or A that will be repeating, or next that comes to B state. So that is this is the, so that is the A. So that is the regular expression. String contains A as the alphabet. So compulsory it requires at least one A. So it's a finite automata. So then here is the same thing we can use. At least 1A, and it will be repeating any number of A's and any number of B's. Here is any number of A's or any number of B's may be like this. Regular language 4. So this is also this. So this is the last one. And next 22. Now you see that gate problems. So now you see the gate problems. I think you are familiar with the theory of computation. That's why I think everyone has understand. I think that. Now you see the gate problems in lexical analysis. So that is, I will explain the 10 problems are there. First you see that the number of tokens in the following C statement is, the number of tokens in the following C statement are, so how many number of tokens are there in the, suppose a print within the double quotes I is equal to percentage D, comma, at the rate of I, address of I is equal to percentage X. So that is, here is double quotes and comma, I comma, address of I, bracket close and semicolon. So in the gate 2000 they got this question. So the printf this one, how many tokens are there? Are 3, are 26, 10 or 21? So which is the correct answer? Which is the correct answer? So for example, here is a, when you see that, so that is a print or something like this. Suppose you say that, so print is a 1 token. You say that print is a 1 token and braces is another token. But here is when you see that, so here is up to this, it is a comment. Already I told you that the entire comment will be considered as a only one string. So within the double quotes, whatever you put within this, it will be considered as 1, and another comma is there, I. So that is the comma, address of I and left or this one. Suppose 1, 2, that is the braces 2, and this comment up to this is 3. This one is the 5, I 6, 7, 8, 9, 10, 11, 12. So suppose here is taken, that is the addresses of this one. So the print of this one, suppose here is a 12 is there. So the print is a 1. See that. That is the answer maybe. So suppose this is a 1. This is 2. Three, comma is 4, 5, another comma 6, 7, 8, bracket 9 and 10. Now you see the answer is C. Now answer is C. Suppose you take the print is a 1. So next brace is 2, up to this is 3, and a comma is 4, and I is 5, comma is 6, 7, 8, 9, 10. So then answer is C. Now you see that answer is 10. So you can use the 10. So that's why here is option C, that is C is the correct answer. But here is the most of the cases in the lexical analyzer. So that definitely you can get this kind of questions. But I have gone through the from so the 99, so that is a 99 to, so that is a 19 gate papers. Most of the papers, so that will having this kind of questions. Count how many number of tokens are there. This is the first question. So the second question, you see that in a compiler, the keywords of a language are recognized during, so during which phase? Suppose during what? Either parsing of the program, B, the code generation, C, the lexical analysis of the program, and D is the data flow analysis. So which one is the correct? In a compiler, the keywords of a language are recognized during Which one? In which page we can recognize the tokens? In the lexical analysis page. That means here is C is the correct answer. So the parsing of the program is, it will check the syntaxes that comes next. So the code generation is the last page. Our next data flow that comes in the, so semantic, also suppose in the case of that code optimization, semantic or something diagrams we can use. The lexical analysis of the program. So answer is C. So that is option for the second one is C. So that is when you go through my notes, definitely you can answer for this kind of statement. All the statements I put in the notes, right? So in the slides. So that is the third question. You see that the lexical analysis for a modern computer language such as Java needs the power of which one of the following mission models in a necessary and sufficient sense. So suppose nowadays we are using the Java. So you can use the Java or Python or R program, you take any programming language. So there is a separate regular expression packages are available. That is the regular statements directly we can solve by using Java as well as Python programming language. Or separate packages are available because so they direct, so for increasing the execution speed, so they incorporated the lexems as a one packages in the one. So first one is the finite automata, second one is the deterministic pushdown automata, and the third one is non-deterministic pushdown automata, and the fourth one is the Turing machines. That is, in the lexical analysis for a modern computer, the modern computer language such as Java needs the power of which one of the following mission models is necessary and sufficient. Which one is sufficient? So that is the finite automata. Just now I explained, you know, NFA, DFA are sufficient for this. So that is the finite automata. So answer option is A. So for the, that is a very simple for conversion NFA to DFA. That's why. So we can use the finite automation. That is the, this is also abstract mission. So fourth one is consider the following statements. Fourth one is consider the following statements. The output of the lexical analyzer is, the output of the lexical analyzer is groups of characters. Groups of characters. This is the one statement. Second one, you see that the total number of tokens in the print in this equation are 11. Just now is 11. And here is third one, the symbol table can be implemented by using arrays and hash tables, but not trees. But not trees. So next that is which of the following statements are correct. Suppose which of the which of the following statements is are correct. Either one or two or something like this. So which one is the correct? Consider the following statements. The output of the lexical analyzer is group of characters. Right? The total number of tokens in a print statement. But just now we have seen it is a total number of only 10. But here is mentioned 11. So this is wrong. That is 1, 2, 3. Suppose when you are taking that, here is total number of. So that means statement 2 is correct, wrong. The symbol table can be implemented by using array and hash table, but not trees. So that is here is the symbol table can be implemented by using arrays, hash tables as well as trees, either binary search trees. So that's why the third statement is also wrong. Why this third statement is wrong? The symbol table can be implemented by using arrays and hash tables, but not trees. But a tree can also used for implementation of symbol table. So that's why here is the A is a correct answer. The A option. So that is the A and that is the 3. So suppose here is also only 1, second, and these two are wrong. And A, so suppose one options you see that A is the only one. Sorry, A is the only one, and sorry, this answer is wrong. A group of characters, not here is the tokens, not a group of tokens. Only one only 2 or 3, all 1, 2, 3, none of this. So that is option is D, sorry. Option is D. Here is the why that option is D. Why can't 1? So the output of the lexical analyzer is a group of characters. So the group of characters is a lexem. Group of characters is a lexem, but the output is token. In the beginning class I explained that. So that's why, so this is wrong. And here is, there are 10 tokens are there, but here is they mentioned 11 tokens. But here is, so the tree cannot be used. They are saying, but tree can also use. That's why, so that is none of the answer is correct, right? So that is all are false. Statement 1, statement 2, statement 3 are false. So next one is already I kept that. Which one of the following statement is false? I will explain that. Which one of the following statement is false? Context-free grammar can be used to specify both lexical analysis and syntactic analysis. Yes, that is correct. That is, so that the context-free grammar can be used to specify both lexical analysis as well as syntactic rules. So then that is in the regular grammar, that is the correct. Type checking is done before the parsing. But actually after parse trace, after constructing the parse trace, after that we are checking the type, data type. So in the pages of compiler I have shown that, no? So int 5, that is the float of 5. So then after constructing the parse tree, next that comes to the next state, that is called, so type checking is this one. So next, high level language performs, high level language programs can be translated to different intermediate representations. So yes, that is the intermediate. High level language programs can be translated to different intermediate representation. This is correct. So that is how many forms I explained in intermediate, intermediate course. Either you can explain triples, or so suppose the postfix notation, or 3 addressing mode. So that is in the different syntax technique. So that is the different ways also there. So C is also correct. Arguments to a function can be passed using the program stack. Yes, that is when you are using the functions. So then, so that is the arguments to the functions will be passed onto the stack. For example, whenever that file in the calling program, whenever it encounters the function call, immediately the address of the next instruction push onto the stack. So after that, the control is directly go to the function, and the function is all the function variables are pushed into the stack and perform the operations. After completion of that execution, so that is when you are using the return statement, again that will comes to the main program of next statement. So that's why here is a D is also correct, but only B is wrong. Why B is wrong? Type checking can be done after the parsing, but not before parsing. That's why. So the answer for this one is the B. The output of the lexical analyzer is. So the output of the lexical analyzer is. What is this? A parse tree. A is the parse tree. B is the intermediate code, and C is a mission code, and D is a stream of tokens. Which one is correct? D is correct. The output of the lexical analyzer is a stream of tokens. The parse tree comes in the next page, intermediate code, that is the next page, mission code, that is the code generation. A stream of tokens is in the lexical analysis phase. So that's why answer is D. Here you can say that answer is D. So consider the following statements related to compiler construction. Statement 1, statement 2. So that is only 1, 2. Okay, right. 4 options are there. Construct the following statement related to the compiler construction. Lexical analysis, 2 statements are there. Lexical analysis is specified by context-free grammars and implemented by push-down automata. Lexical analysis is specified by context-free grammar and implemented by push-down automata. That is the first statement. And the second statement is a syntax analysis is specified by regular expressions and implemented by finite automata. So that is here is the answer is what? Answer is D. Why? Because the lexical analysis is specified by regular expressions and implemented by finite automata. Just now I explained that finite automata, not push down automata. So the syntax analysis is specified by context-free grammar, not regular grammar, and implemented by either finite automata or you can use any push down or anything. Push down automata or finite automata. Here is also we can use the finite automata. So then here is the finite. So suppose this statement is done, reverse that given. Push down automata, finite automata, regular expressions and correct. So that is neither one is true. Neither one nor two is correct. So that means both are false. So that means here is so both are false. Then you see that eighth one. Which of the following statements regarding a linker software is are true? The linkers already, so suppose, but I did not explain. So there are so many translators, so suppose the system softwares are there, loaders, linkers, monitor programs, assemblers are like this. In the program is also, suppose when you are writing the C program, so pre-processing we are using include, include, stdio.h, include match.h, or before that we are writing some macros. So but when you are using that, all the related programs will be linked to our source code by using the linker programs. The linker program or function is to linking the values. So that is, which statement is correct? A function of linker is to combine several object modules into a single load module. A function of a linker is to replace absolute references in an object module by symbolic references to location in other modules. But here is when you are taking these two statements, so which one is the correct? Suppose A, B or C. A specify only A 1 and B specify only 2, C specify both 1 and 2, neither 1 or 2. So here is the function of that linker is, a function of linker is to combine several object modules into a single load module, but it will not use symbolic references. It won't use any pointers or any symbolic references, right? So that's why answer is option is A. Option is A. That is the only one statement is correct and second statement is wrong. Ninth one is that again the same thing I are given. So that is the number of tokens in the following C statements are, so the same thing. So that is the 10. Answer is the 10 we are taking. So then you see that. So here is the given animation. That is the print is a 1. So that is the 2. So that is a 1, 2, 3, 4 up to this value. Here is, I forgotten this comma. You can see that in the previous gate you got the 10, but here is we got only answer is 9. Why answer is 9? But in the previous example I kept I comma address of I, but here is I has been removed. One comma is removed, right? So this is the syntactic error, but previous one they won't show any error. That is the correct statement. So the print 1, this left branches 1. So suppose here is taken. So that is the print 1 and this branches is 2 and the entire thing that will be considered up to this one is 3 and this one is the 4 and I is a 5 and is 6, I is 7 and bracket is 8 and that is 1 is 9. So remember that. So that is the same question, but actually suppose when you put it, so suppose there is a no comma, you see that, here is I did not given comma, so there I give that comma, that's why there I explain 10 and here is only 9. Have understood that? So then answer is 9. So carefully you have to count the tokens. Otherwise, so there may be chances to get the wrong answer. Suppose 9 is there, 10 is there, but in the previous case you got 10 and in this case you got only 9. Why? Because there is no comma. So you need not to bother about that. Simply you count that. If you are getting anything, you can count and you can go to the next place of this one. So debugger is a program. Debugging. Do you know that debugging? Bug means error. Debug means correcting the error. Debugging means correcting the errors. Why it is an error? Bug means a small creature, right? How it is related to error? Do you have any idea about that? Bug. So bug means a small creature. But error is different. But how these two are linking? Why in most of the cases we are using debugging. Debugging means error. Why you got that name means, but when they are using, that is analytical computers, so they constructed that computer with vacuum tubes. Every time they were feeding manually, feeding program manually. While they are executing that, so they got some error. When they got error, they analyze the system. So that is they open the system and they find a small creature. So that is fallen in the one vacuum tube. Because of that bug, so that is they got error. That's why so they change the name of like this. Bugging means that is we are calling that. Because of that small creature, they got error. So after removing that bug from the vacuum tube, they got answer. So that's why bug means you are correcting that error. Debugging means removing the errors. So here is debugging is the program that allows two statements, that allows to examine and modify the content of the register, does not allow execution of the segment of the program, allow to set breakpoints, execute a segmentation of program and display content of the register. Allows to set breakpoints, execute a segment of program and display the content of register. And the fourth one is all of the above. All of the above. So which one is the correct? So that is answer is C. Why? Because allows to you see that either is correct, allows to examine and modify the content of the register. But a debugger cannot modify anything content of the registers. Only it checks whether there is an error or not. So does not allow execution of the segment of the program. But a debugger, so that is it allows the execution of the program, because so suppose in the compiler when you are executing the program, if there are any errors, that error will be thrown to the error handling table and the statement will be executing. So that all the errors after completion of that execution, all the errors will be displayed. So then the B is not, so that is not correct. So allows to set breakpoints, execute statements of program and display the content of register. So this is C is the correct. Why C is the correct means breakpoints. For example, only suppose if you want to execute only a few statements, 10 to 15 statements, we can execute it. But for example, so you see R programming language, the statement by statement you can execute. So we can set the breakpoint. Suppose if the program size is so 10,000, so suppose 1 million statements, if that is divided, that contains the modules, So that is the separate modules we can execute by using some, so that is the conditional statements. Execution of the segment of program and display the contents. That is the debugger will display the error messages or something. So that's why C is correct. A and B are wrong. So that is here is a binary number system. Suppose just briefly I will explain it. On binary regular expressions. So that is only 0 is a regular expression, 1 is a expression in L. So there we use the A and B and expressions. So I don't want to go in depth, but slides are there. See that. Suppose operations are languages. If the concatenation of languages S1 and S2, if there are two languages, we can S1 is equal to S such that S belongs to S1, T belongs to T2. So nth power means this is the formula. Union of L1, L2 or this formula, that means S1 belongs to S1 or S belongs to S2, that is the union. So some of the examples you see that. Two strings, concatenation of two strings. You see that S and T. S is equal to 0, 1, 1. T is equal to 1, 0, 1. ST is equal to, we can combine 0, 0, 1, 1, 0, 1. Or otherwise, this may be first TS. TS is equal to first TS values will becomes and T value next S value. SS means the same S may be concatenated two times. TT S means that is a concatenation, already I explained. This is the string. So L1 is a language using that 0, 0, 1. L2 is a language epsilon 1, double 1, triple 1, dash dash. Any number of ones. It may be having any number of ones. Let you see the gram language L1 and L2. Union of these two. We can union the L1, L2. We can get the answer 0 followed by any number of ones. So I don't want to explain all these things because so time is 5:10. So then you go through this. If there are any doubts, and you call me on the phone, or I can send the doubts like this. But clearly I have given all the examples. So that is the string. So that is 0, 1, 0 star. This one, examples of the strings. The animations are there. Suppose 0 plus 0, we can write the language is 0, 1, or 0 plus 1 star is equal to, that is the language you can form epsilon 0, 1, 2. I explained in the with AB, and here is taken 0 as a any string. Here is string of length is a maximum 1. When you see that this length is the 1, 1, the maximum length is 1. Any string length is any, that is the 0, 1, 2, 3 or any length. Also suppose here is any string that ends with the 0, 1, 0. So that is here is any string that contains the pattern of 0, 1, 0, 1. Suppose if you want to get 0, 1, 0, 1, then you can use the zeros patterns of this one. And here is all the strings whose length is even are multiplied by 3. Suppose 0, 3, 4, 3. So already I explained that with the AP. And for this one, string of the even length, string of length 2 exactly, string of length multiples of 3, string length of multiples of 3. These are the regular expressions we can write. String length of 2 and this one. So these are the examples I have given. So that is, we go through that and we find the results of this. But there is no time. But after that, so this is the thing. So thank you. So thank you for your patience, right? So up to today, I completed that lexical analyzer, and in the tomorrow's class, I can explain. So that is the syntactic phase, and introduction to syntax phase, ambiguity grammar, or next left recursion, right recursion, or different kinds of methods with examples I will explain, right? So thank you. So thank you to all. Thank you, Andy. Hello, sir. Hello, sir. Sir, I'm going to close the session, sir. Okay, thank you, sir. Thank you.